talk too much about those because it's really something you can, if you know the compound and kind of understand how it works, that's all it is, and maybe have one example. I'm not running around looking at, you can tell by the early question, and looking at, you can look at this and say, okay, what's the gas? We already looked at this, alcohol or isopropanol. It's probably going to work this way, and that's all it is. You don't have to know every single compound, and that's why I don't want to spend too much time. You should have heard of them once, but not really that important. So radiation first, and then filtration. So for radiation, there's different ones. There's ionizing radiation and non-ionizing radiation. So the difference is really the power of radiation, and if you have enough power in radiation, if you use these gamma rays, for example, or X-rays, remember how usually the wavelength changes. So you have visible light in say between 5 and 800 nanometers. So towards this end, the waves become wider and less energetic. So on this side of the spectrum, they become more energetic, more and more energetic, and shorter. And to this end, infrared and radio is out there. You have longer waves, less energy. So on this side of the spectrum, gamma and X-ray have a lot of energy, and what they can do is they can cause, actually, that energy can cause electrons to get ejected from the orbit, and you create an ion. And so that's what some of the radiation can do. And there are broad DNA mutations from those. So you have they basically applying this radiation, this high energy radiation, causes mutations in the DNA. And can be used to sterilize medical supplies and food products. So depending on how much energy you can, the material you're sterilizing or disinfecting can take, you use these different radiation. And then here, for example, because we wanted to make sure it's safe and it should have been enough, you go more to the spectrum of visible light, so you're more in that area between 200 and 400 nanometers, and that's UV. And that is not non-ionizing, so it doesn't have the same effect, but it should have still had more effect than it has, to say the least. So what it does, for example, I said it a few times, if you have, and just to make that contrast a little bit stronger, you have, for example, ionizing radiation, and this box or basket was X-rayed, and 5 days later, this is what it looks like, and the same one. Yeah, I didn't conduct the study or have anything to do with it, but I can imagine they basically do these all the time, and they try to keep them under exactly the same conditions besides the X-ray, and I don't know how long they X-ray, but so with food preservation, that's where you can apply these radiation techniques, because you wouldn't want to, heat them up, or there's other techniques you wouldn't want to apply to food. So this is one where radiation is pretty convenient.
What do you think about radiation? I heard a lot of controversy about it. I don't know.
Did I hear that on the radio or? And what station am I listening to? No, I wonder if I read that or heard about it, but I think what it is there's a lot of concern. Not only in this classroom. No, there's concern by the population about radiation, but I think
it's mostly concern for people that don't know.
I think all the scientific. I think that's what it was related to the radiation. All the scientific evidence so far has just shown that it's safe.
Yeah.
So they've done a lot of studies, and usually, I mean, I'm not a I'm not a good person to ask those questions because I usually, as long as it, I don't know, I trust the government too much probably. But what I mean is, I usually I think, oh, they must have gone through so many tests, you know, it's gonna be fine. Because I know that for certain things, it's amazing. If it comes to medication, if you want to bring a new pharmaceutical product onto the market, you think, I would never even go there. I would say, okay, if you don't want it, then I'll keep it to myself. And it takes so much. It takes so many animal studies and, you know, just unbelievable testing. So I imagine they've done a lot of testing to make sure the radiation is
Do they do
safe.
that, like if I were to buy some raspberries at the store, has it maybe been radiated to keep it at the store longer?
I think it has to be indicated on the package. So you would be able to know if it has been or
I
not.
think
Oh,
it's
the little
that.
gray
That
sticker?
Yeah.
Like, oh, that means
That
radiation.
symbol looks like all natural to me.
Yeah.
Exactly. Organic.
Cool. So you see the little rays coming in?
Organic and cheap. Perfect.
You see the rays coming in to the flower?
See, that's what I'm saying. Don't ask me because I would
That's why they're...
I would first eat it and then figure out if I feel different. If not, I would say it's good. I'd probably die early and regret it all, but at least until then I have lived without having to worry about all this
Yeah.
stuff. You can't walk around worry all the
Don't
time.
worry about it.
Teaching a microbiology class and saying, don't worry about it, if you can't see it, it's not going to do it.
That's second row.
It's got to be the quote of the class. Don't worry about it if you can't see it.
Okay, you're kicked off that thing.
So for UV light, just so there must be a direct exposure, and the biggest problem with UV, because energetically or in terms of how much energy comes from this radiation, it's not as energetic, it's not as strong. So you have, as I had to find out personally, you have to expose it directly, and even they say even a piece of paper can actually prevent the radiation, not from completely failing, but from decreasing the effect. So it's really important that it's applied directly. It then usually, in this case, it affects the DNA also, but in a different way. So it's usually leading to pyrimidine dimers. So you have like a bonding of for example, thymine bases, and these bonds just, well, all you have to remember really is that the DNA is affected and that it creates abnormal bonds. So that means as soon as that happens, you would have a stop in being able to replicate the DNA or to read, and so you wouldn't have protein production, and so you would definitely have a loss or a stop in growth, and eventually cell death. I told you about the UV radiation in for example in aquaculture, but this is different. This is this is in a water treatment plant, and the one thing that's important about UV is because the radiation is can work pretty well, but the most important thing is, just like in our experiment, it doesn't penetrate very much, so you have to have you have to basically expose, say, water in this case that you want to sterilize or you want to disinfect by having a lot of surface area. So it doesn't penetrate very far, and so you have to create a big surface area. Maybe in the case of water, you have to have a thin film running and being exposed to UV light. And that's how I imagine. That's how I remember it. We had these pipes, and basically the UV light would just be applied to water running through those pipes in a thin film. So you can look at at this table just to compare the ionizing radiation and the non-ionizing radiation. This one is pretty interesting. There's, I wonder why the American household hasn't seen that too much, or maybe it has, but who has it? Really? Toothbrush? And it goes into
It's for traveling, but.
Wow. Are you sharing with your family? Well, I was always, when I grab a toothbrush and I don't know whose it is, I think it would be good if I had this.
Where are you planning tonight?
In some cases, you have to take a shortcut. So I didn't know you. So, do you know how much that is? Oh, really? And so and it runs throughout the night or whatever. Does it always run when you close it?
No, you turn it on.
Oh, you turn it on. Are there any warnings on it? Like what you should look inside?
Yeah, don't look.
No.
Stay on your
No?
Sanitize.
You're in the middle. You wanna be really careful, but in the end you're not. You go one step higher, but you don't. But then you get the UV problem. And then what I mentioned at the beginning, filtration, the physical removal of microbes using a filter, and you pass a gas or liquid through this filter. And as I said, those are very, they can be very sophisticated. A lot of times I remember filtering water, and I don't know what we were filtering water for that time, long time ago, but you apply a vacuum pump to somehow drain the water to increase the suction, so the water would actually go through. Because you could apply this to a liquid like water and have to wait for hours or days because the filters are so fine. And you can imagine if you wanna filter out microbes. So I think in hospital isolation units, actually, they use it to filter the air that comes in, and it's also used for sensitive liquids where you want to sterilize, but you can't apply heat. So the filtration is still a physical method to use. So this is the final one. This is all physical options you have, or we have like heat or radiation filtering, and then chemical agents is what we use here a little bit to look at differences. And these are the chemical agents, and you've all come across multiple of those. What you want is low concentration and fast action, because a lot of times you just want to wipe your hands, or you want to be able to solve them in water or alcohol if you're a producer, so they're stable and you can sell them in that form. And then some of those characteristics are important. I mean, they're important for skin too, non-staining, but non-corrosive for materials you want to sterilize, and obviously affordable. So you have the different levels, and it's just like what we've seen in other methods. There's high level, intermediate level, and low level, and really again it's about killing endospores or killing fungal spores and a lot of other microorganisms, but not endospores. And the other thing here is these high-level germicides that are chemicals are a lot of times used where you have a device that you can't heat sterilize, but then you intend them, you want to use them in a sterile environment. So your implants or body tissue, you want to put implants in the most sterile way, and sometimes because of the nature of what they're what they're doing, what they're supposed to do in your body, or how complicated they are. You can't apply heat, so you would basically clean them with high level chemicals. So important for this is what's the material made of that you're treating? What's the degree of contamination? Again, the amount of microbes you're expecting. How long can you expose the surface, the microbes on a specific surface to the chemical, and then how strong is it, and what's the mode of action, or what's the reaction? And so we go through these, I think, pretty quickly, just so you've heard about them, and then you can, if you have examples that we used ourselves, I'll point them out, but otherwise you can just, there's a huge list, and it's not necessary for you to know every single chemical agent that's used in microbial control. So these are the ones, and I'm just going to show them here, and then we'll go through each single one for a couple minutes. And I think we looked at those a little bit, and I'll show you how, which chlorhexidine is one of those we used. I put them up here. Alcohols we used. Hydrogen peroxide we used in one of the experiments. Otherwise, detergent, soaps. We used dyes, but not really to kill the microbes, although we probably would have if they were, or we did eventually. So halogens are, if you look at the periodic table, it's usually the group before the last on the right, and you have chlorine, iodine in there, and we use this one. So this one was one of the, and I think it works pretty well for the hand cleansing.
Which one's the iodine?
We just went through this. This was the second to last
No, on the list,
on the table.
339.
More.
Previous slide.
Oh, we'll start from the top. So we'll go all the way.
Halogen.
Is that halogen?
Halogen?
Yeah.
I'm just-
So if you look here, here's chlorine and iodine. So they're usually do 1, 2, 3, 4, 5, 6, 7, 8. So I'll forget about these. So what they do is they denature proteins by disrupting the disulfide bonds. They're used, chlorine, everybody knows, used in water. So you have chlorine added to swimming pools. It's used in wastewater treatment, and iodine, or you've got iodophore, betadine, different terms for it, do the same thing. They're considered intermediate level, so they're and you can tell by what we saw, they're not absolutely the strongest chemicals you can use. Disinfectant, pretty much. And you've seen those either, and you've heard of those either in practical applications or, like I said, in the swimming pools. Those ones, we used Lysol and triclosan in that's the hand soap, I guess. So, and I think they call them phenolics, but the phenol ring is what it's based on. This one, and there are a lot of times if they're used like an antibacterial additive to soaps, they're not as strong. So this one was, I think, the one that we had the most growth after using this soap. So it depends really on the concentration, and Lysol is a little bit stronger, but they're basically having bactericidal, fungicidal, virucidal effects, but don't kill the spores, endospores. They disrupt the cell wall, membrane and precipitated proteins. And like I said, it really depends on what type. There's many different types. Yes. There are many different types of phenolics. So they're based on that phenol ring, but there's many different types, and they differ in their strength. Chlorhexidine, I think was this one. Is it called Hibiclin or Hibitane? So apparently also low to intermediate level. We had pretty good success with it. So this one is a combination. So again, you have these phenol rings. You have two of them, like this, and then you have you have a chlorine also. And so you have a chlorine. It's kind of like a combination of the first two. So the surfactant has protein denaturing properties. They use it mostly for preoperative scrubs, skin cleaning, burns, cleaning up burns. And then if you want to know more details about those, you can, there's a table. One of the basic components that more and more of those hand cleansing agents are using are alcohols. You have ethyl alcohol, which we use here in the lab, or isopropyl, and the difference really is just the length of the carbon. So those ones, the ethyl alcohol contains 2 carbon atoms, and this one has a third. But in the end, it's not a huge difference. I think isopropyl is a little bit cheaper, and you use those to disinfect your tables. So there's surfactants. They dissolve the membrane lipids. Remember the way surfactants are able to interact with the membrane lipids, and so they affect vegetative bacterial cells, and fungi are considered intermediate level chemical agents. Hydrogen peroxide we use. Mainly what happens is with hydrogen peroxide, it produces free radicals, and so it damages protein and DNA and decomposes, producing oxygen gas. So it's toxic to anaerobic or bacteria that metabolize anaerobically. And it's an antiseptic at low concentration, so a lot of times you would apply peroxide to wounds, I think, on a low concentration. And very strong solutions can be sporicidal, so you would actually be able to, if you have a high concentration of hydrogen peroxide, you can create sterile conditions. And I think this one is a small medical device where you actually where you can apply a high concentration of hydrogen peroxide to medical equipment. I haven't seen one of those, but I think there's a picture that's the picture in the book. So you can see how they exactly work, but it basically applies hydrogen peroxide in a high concentration that you wouldn't be handling in this machine to sterilize medical equipment.
What's the concentration of the solution that you apply? It starts with like 2 or 3%.
Yeah, 3, I think, 3%.
So what kind of concentrations are they talking about?
High.
Like higher?
Yeah. I don't know what depends on, I don't know what the machine can take.
The machine makes it a higher concentration?
No, I think you can get higher concentration. It's just what's it's a question again of what you're sterilizing and for how long, etc. So when you know the device you're using, and you have a certain amount of time, that's going to be, depending on that, you're going to adjust the concentration of peroxide. 35? Aldehydes, they have a group that, I'm not going to write that down, but it's basically a specific group on there, the molecules end with a specific group, and what that does is it can cross-link to proteins and DNA by linking to microbial proteins. So basically, if you have an outer membrane, in this case has to be a gram-negative organism, microorganism, or gram-positive. In this case, you have the cell wall, and what this group does, it can link, or it can bind to those proteins, and therefore,
Like a competitive.
yeah. Well, it just attaching to it is gonna change. It's gonna change the regular. It's not. Maybe it might be competitive with anything else the cell binds to, but it's basically a compound binding to the membrane or to the cell wall, and so it's going to change the processes that are happening. It's used for heat-sensitive instruments. Another one of those is formaldehyde gas. I don't know if you're familiar with formaldehyde or formalin. So formalin would be a solution, an active solution of formaldehyde. And so through that process, it creates an intermediate to high level of sterilization or level of disinfecting. Butanol? Yeah. So what you usually do is that, yeah, and it's not you use it a lot too. Formalin it's not good to breathe in. I think it's listed. So you have to always work under the hood. You work under the hood with the formalin, or did you have?
No, we sprayed it on the cadavers for preservation.
Okay.
Because I think what it does, it binds to the.
Yeah, it preserves that's what. You can even use formalin in a container, and basically, I can imagine that some of those are in formalin. Like basically preserve everything. But it also means you have no microbial decomposition of your specimen either. So that's a big part. But it does preserve everything, all the structure. So if you do anatomy, you want to be able to recognize the specific structures. Then you have gases and aerosols. So a lot of times when you're in the industry, when you try to disinfect package material, for example, you use those, and this was an ethylene oxide sterilizer. You're not going to get in contact. It's just with one of those. It's just another application of specific chemical compounds to sterilize or disinfect, and then it's used in the food industry in pre-packaging. And you can look at the specifics for that too, if you want, but it's not going to apply to most of the things you do. And then detergents and soaps, they usually act as surfactants and alter the membrane permeability of some bacteria and fungi. So you can tell that they're usually not so their level is very low. What they usually do is they have a positive head and a long hydrocarbon chain, and so the positive head, just like the cations we use for staining, are binding to the negatively charged bacterial surface, and then this chain disrupts the cell membrane. But as I said, it's the efficiency or the effects of that of detergents and soaps in terms of trying to disinfect or sterilize is very low. And then for soaps, the same thing. Their efficiency is very low. You basically remove mechanically soil and grease and the microbes that come with it, but you're not really, a lot of times, like we've seen with this soap, you're not really killing, like with this one, you're not really killing microbes, you're mainly just removing them mechanically and lowering the concentration.
So, we have surfactants in our like lungs. Is that just to kind of mechanically, like if we cough, move it out of our lungs?
No, the term surfactant is a combination of 3 words, and you can, so it's not, the surfactant doesn't mean it's a specific compound, so it's
Okay.
just
Kind of
it's a surface attaching something. So
that kind of protects it.
yeah. So in the lung, it's a I remember, man, it's a long time ago. I have to look that up because I remember it's connected to some disease,
Okay.
but it has nothing to do with the microbial world.
Alright.
I'll tell you in 5 minutes. And then heavy metals are pretty much one of the last ones, and they have, and I think we've looked at it initially. If you have a protein, heavy metals can attach to the active site and inactivate proteins throughout binding to the active site, and you have this plate where you can see that applying these heavy metals leads to a decrease in growth, but they're also low level. They're not, you wouldn't find them very often in disinfectants or sterilizing chemicals. And it shows you here in the table in the book what these are for. Dyes, we use those, they're usually, there's specific ones that can work against bacteria and different fungi. They're sometimes used for antisepsis and wound treatment, but they're very low level and they have a very narrow spectrum. So their activity or the application of dyes is very limited, and I don't remember ever coming across those for disinfecting, and they're staining, so that's another negative characteristic of dyes. So you don't really see those used as antimicrobial agents too much. Acids and alkalis, they have a low, again, those are all, the last few ones are all low level in activity. They kind of prevent germination and growth, but they're not actually killing the microbes. And there's different ones. Some prevent growth of anaerobic bacteria. Some inhibit the growth of yeast. And you can at the end of all this, like when you've gone through the list and kind of try to figure out, or when you go over this list one more time and look at what have we looked at and what's out there, especially if you're interested in for your own foreign use, you can go to this table and look at the active ingredients and then really what the chemical agent is, which usually is indicated on the bottle, and then what the category is, and then you can look it up in those tables and figure out what their mode of action is and what it does. And that's it for physical and chemical microbial control. So you can, does everybody know how this works today? I mean, we have